Hello everyone, this is the second part of our video. Hello everyone, this is the second video in our playlist, and in this video we're going to look at a very interesting example of a wind turbine. And we're given a question which says, for a turbine generating power from a flowing fluid, use momentum and kinetic energy balances to show that the maximum power generation, assuming perfect efficiency, difference in kinetic energy in inlet-outlet flow is converted entirely to useful work, occurs when the ratio of an outlet to inlet velocity is 1/3. Okay, so here we have a diagram of a windmill. So we have air going into the windmill and air going out of the windmill at some particular velocity. And it is obvious that the velocity is gonna decrease because of the fact some of the velocity is going to be converted to kinetic energy, and it's going to be converted to some power using the windmill. And because of the decrease in velocity, the area is going to increase. Okay, so here let's consider, for our particular problem, let's consider the mass flow rate of air in 3 particular points. So let's say this is the first point and this is the second point, right? When it's going in and going out. And here we're going to have some velocity, right? Which is going to be converted to power. And if we multiply it by density and S, which is the perimeter of a windmill, it's going to be the mass flow rate of air going in. And at this particular point, like for the flow going into the turbine, it's going to be rho times the velocity 1, velocity 1 times the area 1, right? And here it's going to be the rho times the velocity 2 times the area of 2. And the density is going to be the same because it's still the air, nothing is changing. Okay, so, and adjusting the gear. So what is going to happen in our problem is, so if we adjust the gearing, it really affects how much velocity is going to be converted to power. So we're assuming that we have a perfect gearing ratio, and we want to find out the maximum power that can be generated from the air, like the maximum amount of power that can be generated to power, maximum power we can get. Okay, let's consider the momentum balance for our particular scenario. Momentum balance. Okay, so our momentum is going to be our dmv, derivative of a mass times velocity over time. So it's going to be, we're considering a partial momentum at a specific time of a system is going to be equal to velocity going in times the mass flow rate going in, right, minus the velocity going out times the mass flow rate that is going out, and plus the force. So there's going to be force on the blades from the air, right? Or it can be also considered as a force from the blades to the air. Depending on which one we're considering, we're going to change the signs. Okay, we're considering it to be in a steady state to make our problem easier, which means the whole thing is going to be equal to 0. So the steady state means there is no change in time, like respect to time, right? So we're going to say like the momentum is not changing respect to time, so it's going to be equal to 0. And we know that our mass flow rate is equal to the mass flow rate in, which is equal to the mass flow rate out, right? So if we manipulate this equation and make the force as the subject of equation, we're going to have negative force is equal to velocity. So velocity that's going in, it's going to be our velocity 1 minus velocity 2 times the mass flow rate, which is going to be this thing, right? Rho density times S times the V, right? Okay, and again the force is negative because we're considering the force of air to the blades, right? That's why we're going to consider the negative force. And if we talk about the power, we know that the power is equal to force times the velocity, right? And in our problem, it's going to be the negative force because of this, because of the force we're considering. And we also have to consider the assumption that the direction of a velocity is in the same direction of a force. Okay, and if we replace the whole equation to our power equation, we're going to get power is equal to V1 minus V2 times the density S velocity squared, right? Okay, so this is the momentum balance for our scenario. Now let's do the kinetic energy balance. Okay, kinetic energy balance. Okay, so we're going to be considering the kinetic energy per unit mass, and we are assuming that the assumption we made when we started the question was the difference in kinetic energy of inlet and outlet flow is converted entirely to the power. So which means our power is going to be the change in kinetic energy over mass. So we're considering the kinetic energy per unit mass times the mass flow rate, right? Okay, so we know our kinetic energy is 1/2 mv squared. So the change in kinetic energy is going to be 1/2 m v2 squared minus v1 squared, and we're going to have m in numerator and m in denominator, so it's going to be cancelled. So the power equation we're going to have after we substitute the kinetic energy equation is v2 squared minus v1 squared over 2. The masses are going to get cancelled. So the mass flow rate is density times S times velocity, right? Okay, so this power here is equal to this power, right? So what we're going to do now is we're going to make these two equations equal to each other. Okay. So we're going to consider this and this equation, right? So it is V1 minus V2 rho S squared is equal to V2 squared minus V1 squared speed, right? So this is going to get cancelled, velocity is going to get cancelled. So let's try to solve for V. Let's try to find out what our V is equal to. So we know that our V1 and V2, but we don't know what our V is equal to, right? Okay, so if we make V the subjective equation, we're going to have V2 squared minus V1 squared over 2 times V1 minus V2, right? Yes. So we can simplify the numerator. So if we open it into two brackets, we know that V2 squared minus V1 squared is equal to V2 plus V1, V2 minus V1. And 2 times V1 minus V2, right? So the change of velocities. So we can clearly see that they are going to get cancelled, and what we are left with is now we want like the sum of two velocities over 2. So isn't it cool that the velocity that's going to the blades is just the average velocity of that is going in and out. So it was something obvious, but we derived it using the equations. Okay, and now what we're gonna do is, what we can do here is, we're gonna replace this to our power equation we derived from, to our power equation we derived from kinetic energy balance. So we're gonna have our power to be equal to V2 squared minus V1 squared over 2 times the rho s times V, which is going to be V2 plus V1 over 2, right? Okay, let's simplify it and have all of our velocities, like we can actually multiply the velocities and have a new expression for power. So we're going to have rho s over 2, and it's going to be over 4 because we have two 2's, and we can multiply this to this here, like the velocity. So we're going to have velocity 1 cubed plus velocity 1 squared, velocity 2 minus velocity 1 plus velocity 2 squared and minus velocity 2 cubed, right? So that's what that's the expression we're gonna have for the power. Okay, what we can do now is we can get velocity cubed outside of the parentheses, so we can factorize it. So what we're gonna have then is rho s over 4 velocity 1 cubed, right? It's gonna be 1 plus, so velocity velocity squared and velocity cubed are gonna be cancelled, so velocity 2 over velocity 1 minus velocity 2 squared. Okay, it's gonna be this, right? Minus, so we're gonna just have to, okay, if we consider these now, they're the ratio between the velocity 2 and velocity 1, right? Let's make it r, velocity 2 over velocity 1, right? Okay, so that's what the gearing is about. So depending on how you adjust the gearing, you're gonna get a different ratio to the velocity going in and then out. So now we're trying to find out that in order to have all the kinetic energy being converted to power, we're going to calculate the rate. So for the maximum power, we're going to calculate the ratio of two velocities. So we're going to change those V2 over V1 to R minus R squared minus R cubed. Okay, and in order to find the maximum power, we need to take a derivative. So what we're going to do is we're going to take a derivative of power with respect to R, and we're going to have rho s cubed. This is going to be the constant, and here it's going to be 1 minus 2R minus 3R squared, right? Okay, and we're going to make that equal to 0 to solve for the ratio, right? In order to find maximum power, we're going to get the slope. It's kind of like slope where it's going to be equal to 0, which is going to be the maximum point. So if we factorize it, it's going to be 1 minus 3R, 1 plus R is equal to 0, and we're going to solve for the value of R, which is going to make our equation equal to 0. And here, from this, we're going to get a -1. R is equal to -1, but we cannot have R to be equal to -1 because our ratio cannot be like, the air cannot flow in other directions. So we're going to consider this where our R is going to be equal to 1 over 3, which is 1/3. So the problem was stating to prove that the ratio of outlet to inlet velocity is 1/3, which we now proved, right? Okay, what we can do now is we can try to calculate the ratio of maximum amount of power we can get from this gearing ratio. Okay, so what we're going to do is we're going to get the power is equal to rho SV cubed over 4, and we're going to substitute r's to the equation. So it's 1 plus 1/3 minus 1/9. Okay, so what we're gonna have here is, so this thing is gonna be 32/27, and we know that the maximum power is rho SV1 v squared over 2, right? So it's gonna be 32/27 times 1/2, because here we have 1/4, like 4, right? But the maximum power is 2, so we're gonna get our 1/2 inside of a parentheses. So the ratio of maximum power is, not the ratio, like the maximum power we can get is gonna be 16/27. So if we assume the perfect ratio and the the perfect efficiency, we can only get 16/27 of the maximum power. So in this problem we looked at a very beautiful example of a windmill, and we learned the momentum balance and kinetic energy balance behind the windmill to find the ratio between the outlet and an inlet velocities. Thanks for your attention.